day, everyone. For this presentation, I'll just give a brief introduction of Module 3. And these are the objectives for Module 3. And for today, I'll just give a brief review of heat transfer mechanisms in the atmosphere. First, let's recall some important terminologies. Number one is temperature. So temperature is a measure of kinetic energy of the atoms and molecules. So it involves the movement of these atoms and molecules. So the higher the temperature correspond to faster average speed. So as recall, kinetic energy describes the energetic movement of these atoms, and it's proportional to the speed of this atom. And then heat. So heat is energy in the process of being transferred from one object to another because of the temperature difference between them. So if there's temperature gradient between two objects or other medium, so there will be a transfer of heat. And not only that, energy heat is also energy used to change the phase of a substance. So it doesn't have to have a difference or a temperature gradient. If you change the phase of a substance, then energy is used to do that. Okay. And another important term that we will use for module 3 is the word insolation. So insolation is a measure of the solar energy that is incident on a specific area over a set period of time. So basically, it's just the intensity or the power of the solar energy hitting an area over an entire year. So it can be a measure of annual solar energy. This is very important, because this actually explains why the heating in the equator is much higher than the heating over the poles, the two poles, and hence it causes circulations, in the atmosphere. But anyway, so this is insulation. We have temperature, heat, and insulation. Now, how is this energy transfer process accomplished in the atmosphere? Okay, so recall the temperature profile of the Earth, of the atmosphere, in particular, as compared to pressure and density. The temperature of the atmosphere is not uniform all throughout. No, the temperature profile, for example, in the troposphere, is actually decreasing because the heat comes from the surface. So as the sun heats, so all energy comes from the sun hits the surface of the earth, and then the earth cools down, and it also, as it cools down, it releases heat, in terms of long wave radiation. So later we will discuss more about this radiation from the sun and radiation from the earth's surface. And another thermodynamic principles that govern the temperature profile of the troposphere is given here, the Charles law. So basically, air is compressible as we know it. That's why there's more temperature, there's more air, the density is higher near the surface because of the pull of the gravity. So it decreases with height. So the rising air expands as it rises, and when it expands, as we know, when gas expand, it also cool down. Okay, so that's why we have this temperature profile in the troposphere. And again, in the stratosphere, we know that there was an inversion. There was an inversion of the temperature profile, so it's now increasing with height. And this is because of the ozone layer near the middle of the stratosphere. So ozone layer absorb UV radiation from the sun, and it radiates heat in all the direction, downward and upward. That's why in the mesosphere, mesosphere is also affected by this ozone layer. So the heat is radiated from down the mesosphere, okay, and also the pressure there is very low. The air is also very thin to transfer the heat, the atoms or molecules to transfer the heat is quite very weak at this sphere. And then in the thermosphere naman, where there is an extreme ultraviolet radiation, and this radiation, UV radiation, is absorbed naman by molecular and atomic oxygen. So notice, no, the stratosphere and the thermosphere basically have the same structure, while the troposphere and mesosphere have the same structure. So basically, what's common, you know, with this profiles is that it depends. So the profile depends on the source and on the direction of heat. Okay, so where is the direction of heat transfer, or where is the source of heat transfer? Okay. Similarly, um, the, we also have a horizontal structure, you know, for temperature. So temperature changes with height and also with latitude. That's why in the equator we have a thicker, let's say, troposphere as compared to the South Pole and North Pole, because the heating in the equator, you know, or the insulation in the equator is much higher than that in higher latitudes. Okay, so basically we call this differential heating. So differential heating, so the heating is different. The intensity of the heating is different. Okay. Again, no, overall temperature changes with height and latitude, and this is because due to the on the source and direction of heat transfer. Okay. Now, what are the ways in which heat is transferred into and through the Earth's atmosphere and surface? So there are several mechanisms of heat transfer, and in the atmosphere, um, on the surface, no, near the surface, and in the atmosphere, uh, there are at least four important heat transfer mechanisms. Of course, the first one is the radiation. The sun hits the ground through radiation, and then on the surface of the ground, the air is heated through conduction. And then the warm air rises even higher, and most of the time it brings with it moisture through convection. And then uh, everywhere, you know, if there's changes in phase, let's say inside a cloud, you know, there are many change, phase change happening in the clouds. So there's another transfer of heat, you know, the latent heat transfer. So let's define first, you know, this heat transfer mechanisms. So conduction is the transfer of heat energy from one substance to another or within a substance. So there should be a contact, you know, between this substance um, to transfer the heat. So the closer the closer the molecules, you know, of the substance, the higher the heat capacity or the conducting capacity of the substance. Okay, and then convection, no, the transfer of heat energy by the mass movement of fluid. Now, advection, so convection is a vertical movement, no? While advection, on the other hand, it's also similar to convection. However, advection is horizontal movement. So this is actually define our wind currents. You know? So it's actually the same mechanism, except that advection is differential in the horizontal direction. Then, of course, latent heating, no? Exchange of heat as a result of changes in the phase. Well, we will talk about phase change of water in the atmosphere. No? So it's also known as the hidden or stored energy released during phase change. And lastly, one of the most important heat transfer, of course, is radiation, the transfer of energy through space by electromagnetic radiation. Okay, so let's start with conduction in the atmosphere. No? So again, with conduction, there should be a direct contact. So molecules bump into one another, and then in the process transfer that heat. Um, Earth's surface conducts heat to the atmosphere through air molecules. So remember, no, air molecules in the surface is more compact than higher level molecules. So somehow, no, that close contact of air molecules near the surface help to conduct the heat. You know, as the Earth cools down, it radiates heat. So that heat, you know, is being conducted by the air molecules near the surface of the Earth, you know, around. But then again, of course, air is a poor conductor. So conduction in the atmosphere is only limited. It's only can only be observed near the surface of the Earth. Okay. So again, air is compressible and decreases with height. So as you go up, conduction is cannot really transfer heat, no, or the conduction is very weak. Conduction of heat is very weak as you go up. No? So again, air is a poor conductor. So conduction, heat conduction occurs mostly at the Earth surface, but it's a very important heat transfer, no? Because without conduction, anong mangyayari? Anong mangyayari as bigla nilang mawawala yung heat. As the Earth cools down, tapos walang conduction, mawawala yung heat. So you can imagine how lower the temperature is. So heat flows, no, usually from warm area to cooler area. Okay. So what happens is at night, you know, as the ground cools, so during the day, sunlight, the sun hits the earth, and then during the night, mag-cool down na ang earth. You know, so the cold ground conducts heat away from the adjacent air. Okay, so ang nangyayari niyan, since mas malamig na yung ground, you know, it conducts heat away from the adjacent air. That's why malamig, di ba, pag gabi. During the day, again, no, solar radiation hits the ground, so it hits the air next to it by conduction. So mainit. That's why mainit pag tanghali, no? At least near the surface of near the ground. Okay. So again, so the other form of conduction. So as you go higher, hindi na pwede yung conduction, no? So the other forms of heat transfer is convection, or the vertical movement of heat, you know, with moisture in the atmosphere. So basically, convection happens when there's an even heated surface. And as we know, no, the uneven heated surface is due to conduction. So may conduction ka dyan, and there's an uneven heated surface, so nagkakaroon ng low pressure. So pag may hot surface ka dyan, and then maybe the surrounding has lower pressure, magkakaroon ng higher pressure, magkakaroon ng low pressure. And that low pressure will cause the movement, no? Up, or the rising movement of air. So air rises, no, from the warm ground, basically warm ground to cooler air. So pataas, because that's the temperature profile of the troposphere, diba? Cooler siya. So yun yung tendency ng air, okay, para mag-stabilize siya. Okay. So air expands, and then thermodynamically, no, air expands as it go up, no, it cools down, it expands, and if enough water vapor is present, there's a possibility of formation of clouds, no, during convection. Okay, so there are many types of convection. So one good example is examples are this hot air thermals. No? We call this air bubbles or thermals. No? So these thermals basically are column of rising air. No? So near the surface, maliliit lang yan na hot air bubbles. Let's say bubbles, no? Air bubbles. And then as it rises up, they bump into each other, and then they form into a bigger air bubbles. Let's say bubbles, no, but bigger. So they are called thermals. Okay. So at the top of these air thermals, no, there's an unstable atmosphere over here, and then there's enough moisture that rises up, due to these thermals, then we expect some cumulus clouds, on top. And sometimes when there are many uneven hot thermals, on the surface, magkakasunod din yung mga cumulus clouds na yan. Okay. So another examples of convection is when warm air, when warm air is rising and then as it rises, bumps into, let's say, a barrier. And in this case, in this example, we have a mountain. So uh, it's a fluid, gas. So as it bumps to this mountain, this warm air will rise. As it rises, there's a pull again, the temperature profile of the troposphere. So cooler siya up, so it will cool down. So as it cools down, there's condensation, and then it could lead to formation of clouds, etc. Then it will sink. When it sinks, it warms up. Okay, so this is just an introduction of atmospheric moisture. Later on, we will discuss this further. Sorry about that. Okay. So warm air rise, as it rise, it expands and cool down, following this thermodynamic uh, relationships, between pressure, volume, and temperature. So as cold air sink, meaning ano na siya, it started to contract, So it shrinks and then warms up. So may tawag dyan actually. But anyway, this is a form of convection that can lead to the formation of clouds and probably precipitation, in terms of snow or rainfall. Okay, so that's convection. Another very important examples of systems formed through convections are the convective cells. But notice that this particular Earth, is a simplified smooth Earth, with no lands interaction. So this is the one of the most simple representation of how convective cells were created. So basically, you have a differential heating. It's warmer in the equator, so and then it's colder in the higher latitude. So there's a warm air here, and then there's cold air surrounding this warm air. So ang tendency ng air, there will so magkakaroon ng mga low pressure area dyan. So ang tendency, if it's low pressure, mag-rise, air will rise with low pressure area. So warm, light air at the equator rises and spreads northward and southward. So as they go up kasi, na ay ano lang dyan, they will eventually spread out. Okay, so may so may tinatawag tayo na top of the cloud top. Okay, cloud top. So at that level, hindi na kayang tumaas pa ng clouds, So at that point, mag-spread na northward yung itong rising air natin. Okay, so it spread. And then in the lower, at the North Pole, you have this lower high pressure area. So the air will start to sink. Okay. So with this rising air here in the equator uh, produces convective cells. Okay, so air is replaced by the surrounding cooler air more dense. So this so as the air, the warm air rises, it spreads horizontally, and that causes actually the wind. So yeah, and then at the pole it will sink. So basically, this is a very simple representation of convective cells around the globe. Note, however, na yung mga, let's say, yung mga convective cells natin like the ITCZ, it's not really at the equator, off siya. That is because there are other parameters here. So we have to consider the rotation of the Earth, Coriolis effect, etc. No? So marami pa, rotation of the Earth, the tilt of the Earth, ganyan. So there are other mechanisms, but so basically this is how the convective cells around the Earth, or the atmospheric convective systems are formed. So you have a low pressure area that rises, and then uh, that rising low pressure area brings with it, brings with it moisture, that eventually cools down and will form convective, let's say, clouds. So yeah. So of course, aside from convections, there are other parameters that causes convective cells. Let's say some systems that bring precipitation. Hindi lang siya convection. There are also meron ding convergence, of wind. But we will discuss that in the atmospheric circulation part. So this is just a simple examples of convective cells around the Earth. And then the third mechanism is latent heating. Okay, so latent heating is the exchange of heat as a result of changes in the phase of water. Okay, so it's the hidden or stored energy released during the phase change. Okay. So these are the examples of this phase change. Evaporation, for instance, is changes of water or liquid phase to vapor or gas phase, and so on. Diba? The inverse is condensation. Then we have sublimation. The inverse is deposition. Then we also have melting. The inverse process is the freezing. And all these processes releases latent heating. However, they actually have a impact, uh, to the environment, to its environment. It's either they give release the energy used to change the phase of a substance without changing the temperature. So recall, the definition of heat. Heat is the energy released when there's a difference in temperature between let's say, two objects, or two medium, two systems. But it's but for this one, latent heat, it's actually the energy that is used to change the phase, and not to change the temperature. Like at the point of when there's no difference, within water and vapor during evaporation, at that phase of evaporation, let's call it phase of evaporation, the temperature is actually constant. Okay, so there are two effects, to the environment. First, the cooling effect. Heat is absorbed by the substance and taken away from the environment. So it has a cooling effect, so among this, the cooling effect is the melting, evaporation, and sublimation. So melting, so let's say, from ice to liquid, evaporation uh, from liquid to gas, and the sublimation is from ice to vapor, or gas. So the common denominator of this processes is that from compact molecular structure to less compact. So it needs more energy. It needs energy to cut that bond between these molecules and make it a more the movement. So basically, yung kinetic energy, mag-i-increase ka ng kinetic energy among molecules. Diba? From ice to liquid. So ice it's halos hindi gumagalaw, or hindi talaga gumagalaw, and then it will melt. So gagalaw na yan siya, mas maluwag na siya. Yung kinetic energy niya so kailangan niya ng malaking kinetic energy para mag-move out from the solid phase. So parang ganon. So from compact to less compact molecular structure, it needs energy. So it will take away or absorb heat from the environment. So it has a cooling effect. So this processes have a cooling effect. And then, of course, there's the opposite processes of melting, evaporation, and sublimations. On the other hand, have a warming effect because from less compact structure to more compact. So they will basically release heat energy to the environment. So the freezing, condensation, and deposition have a warming effect to the environment. So for instance, the latent heat of evaporation, so it has a cooling effect. The energy needed to evaporate or loosen the water molecules may come from the water itself or other sources, including the air. Okay. Again, note that the temperature uh, of the substance changing from liquid to vapor is still the same, is constant actually. So the heat energy that we feel during parang nakikita natin na nag-change ng phase is actually sensible heat. It's not the latent heat. Okay? So latent heating is very important to atmospheric processes because it gives out energy, to these atmospheric systems. For example, the large convective systems, tropical cyclone intensification, thunderstorm, mid-latitude cyclones. So these systems are very much can be energized or they can be weakened, by several processes that release or that release latent heat. Okay, so should not be the third, but the fourth heat transfer mechanism that we will discuss is radiation. So again, radiation is the transfer of heat energy through space by electromagnetic radiation. So basically, we will just focus on that heat transfer between the sun, the atmosphere, and the Earth's surface. Okay, so the radiations coming from the suns that usually can make it through our atmosphere are the UV visible light, and the other radiation, of course, are somehow being filtered, but there are still few that can pass through the atmosphere. But these are just examples of UV visible light. So basically, the shorter wavelengths, comes from the sun, and then the infrared thermal radiation. Usually, these are the radiation that the Earth can release, to space. Okay. The solar energy moves through empty space from the sun to the earth through radiation. Okay, and on the other hand, Earth's irradiate long-wave radiation towards the space. So how can Earth's radiate back this energy to the surface? So note that this is different. This one, the long-wave radiation from the Earth, is different from the radiation coming from the core of the Earth. Okay, so that energy from the core of the Earth, on the other hand, fuels the movement, in the solid Earth, in our geosphere. While this one, this long-wave radiation from the Earth radiation is the can so the term here, we are using it as a form of heat transfer, and of course, it's also synonymous, or it's also being used to as a form of energy, but let's call it radiant energy. Okay, so in talking about in discussing radiant energy between the sun and the earth, it's important to understand black body radiation. So what is black body radiation? This is the thermal radiation within or surrounding a body in thermodynamic equilibrium with its environment or emitted by a black body. Most of the energy here is infrared and thermal radiation. So a black body diagram, a black body is an opaque, body and a non-reflected body that absorb and radiate energy. So basically, there's an incoming radiation, and then it has the ability to re-radiate this as an outgoing radiation. So there is balance. Black hole is an example of a perfect black body, and then the sun and the planets are also example of black body, but these are not perfect black body, especially the planets, because of there are many impurities, with with our planets. Okay, so but the perfect one is the black hole. Okay? So if you have a black body, it absorb radiations, and it also re-radiate this radiation, and most of the time most of this energy are infrared or thermal radiation. Okay, so let's now compare solar radiation and planets. Okay, so you have an incoming solar radiation. On top of the atmosphere, this solar radiation is actually constant. Okay, it's constant because it's almost sobrang layo. Let's say the sobrang layo ng mga planets from the sun, as compared to its radiating out, in space. Halos parallel na siya. So yung nakukuha actually natin na solar radiation is constant. However, the radiative heating or the insolation is different, depending on the surface. So the sun and the earth are approximately black body, and these black bodies are actually governed by this universal law, the Stephen Boltzmann law for black bodies, which is given by this equation. And through this equation, so this is S is just the energy emitted or absorbed, and this and with the effect of the surface, the albedo effect. Albedo is just the reflectivity of the surface to solar radiation. Okay. So using this equation, we can actually calculate the average temperature of that particular black body. Okay. Okay. So before that, aside from the Boltzmann's law, the Stephen Boltzmann's law, the sun and the earth also follows the Wien's law, okay, wherein hotter objects radiate energy at a shorter wavelength than cooler bodies. So comparing the two, sun is much hotter than the earth. So if you notice the wavelength, so this graph shows the wavelengths, in the x-axis, and then the intensity of radiation in the y-axis. So if notice that first, in terms of radiation intensity, we can see that the sun, the peak of intensity shorter wavelength, just like the sun, than polar bodies, just like the Earth. So the sun's radiation intensity is much higher than the Earth, and the sun's radiations are much shorter also, as compared to the Earth. Okay. Yeah, so as the wavelength decreases, the energy carried per wave also increases. Okay, so this is Wien's law. Okay, so this is just to show you that EM wave spectrum is actually wider, but what's we can be seen by our eye is just the visible, which also have a shorter wavelength and longer wavelength. But note that the shorter wavelength, gamma rays, X rays, UV rays, these are most of the wavelengths that the sun emits. While on the other hand, the longer wavelengths, are the wavelengths that the Earth mostly emits. For black bodies, we can actually get the average temperature of the Earth. Okay, so let's look at the average temperature of the Earth and maybe other planets also. So notice, Mercury, this is Mercury, Venus, Earth, and Mars. You can see the respective temperature, in Kelvin and in Celsius, degrees Celsius, and these are the alpha represent basically the albedo, effect of the surface of this planet. And notice the TP, which is basically the uh, calculated from the Boltzmann, Stephen Boltzmann's law, while the T observed is the observed, using instruments. Notice the big difference, of this um, temperature, specifically, for the Earth. You can see that it should be negative 18 degrees Celsius, but what is observed globally is actually 15 degrees Celsius. So it's actually the same fate with other planets. There is discrepancy between observed and the law, the theoretical um, law, for calculating the temperature of these planets. So as I've written in your classwork, next meeting, I want you to explain what causes this anomaly on the Stephen Boltzmann law for block bodies. Remember, this is a universal law. Stephen Boltzmann is a universal law. So how can we explain this anomaly? Okay. So what does the Earth has, or this other planet have, that causes this anomaly in the average temperature? Okay, so we will discuss this in our next meeting. Thank you.